Y19 light waves. Electromagnetic wave, light wave is a kind of electromagnetic waves that follows the rules that is governed by the Maxwell's equations. An electromagnetic wave can propagate in a medium, for example, air, glass, and many medium. However, it can also travel, propagate in vacuum. It does not require any medium, even though in some cases it travels inside a medium. When it travels in a medium, in vacuum, the speed of light is fixed, and this number is exact. It has two polarization states that are transverse relative to the direction of propagation that is represented by the wave vector. So this one is the square root mu 0 epsilon 0. And it was first noticed by James Clerk Maxwell. Okay, first let us consider a wave. This is amplitude, wave number, angular frequency. This can always be expressed as sine k x minus vt, and his v equals omega over k. Therefore, it satisfies the one-dimensional wave equation. The directional propagation is along the x-axis. Because it's a negative sign, it is going forward. If it is in this form, then it propagates along the negative direction. Because there is no description, no further description right now, I don't know whether it is a longitudinal wave or transverse wave. Need more description to determine. This wave is a monochromatic with a wavelength lambda. Wavelength is fixed and the angular frequency, the frequency are fixed constant. So in that case, we say single wavelength wave is called monochromatic, single color. The speed of this wave is completely determined by this relation. Yes, right. We consider the interference of two sinusoidal waves with a finite phase difference. First of all, these two waves has a common speed of propagation. They are traveling along the same direction. Anyway, if I write these two and add them, then we can simplify. Perhaps we have the relation far below. No, we learned many times before. So sum of two sines, sum of two cosines, sum of two exponentials with the phase difference phi, then the average of these two is this plus 1/2 of phase difference, and this function is identical to those, and the overall factor is 2 times a cosine half of pi. So we have to remember, in case we have cosine, kx minus omega t, kx minus omega t plus phi, in that case, everything will be the same except that this one is to be replaced with cosine. In case we have e to the I kx minus omega t and e to the I kx minus omega t plus phi, then everything will be the same except that this one is to be replaced with kx minus omega t plus 1/2 of phi. These are given in here, all set. The phase of the resultant wave, this one is called the resultant wave, is 1/2 of the difference, between the two phases. The resultant amplitude is doubled when the phase difference is vanishing. Yes, cosine half of phi equals 1 when half of phi equals not only 1, but also, as far as amplitude is concerned. So cosine becomes a plus minus 1 when it is n pi. Therefore, phase difference 2n pi, 0, 2 pi, 4 pi, plus minus. In that case, they make double amplitude, that is called completely constructive interference. It is possible to have exact cancellation that appears when 1/2 of phi equals pi, 3 pi, plus minus, and so on. So these are even numbers of pi. These are odd multiples of pi. Odd multiples of, wait a second. This is pi. This is half of pi. So constructive, destructive, constructive, even times pi, odd times pi. Okay? What is phi equals? Find the full statement regarding the light wave propagating in a medium. Single medium, a plain light wave propagates as, right now we consider electric field only. And as we know, propagating magnetic field comes from the electric field as a carbon copy of the amplitude. E and CB, they are in equal magnitude, and the direction is completely determined as X, Y, and Z axis, where K behaves like the Z axis. So it is sufficient to consider the electric field Remaining pieces are completely determined automatically due to the Maxwell's equations. We have some function, sinusoidal function, monochromatic sinusoidal function, cosine or sine or e to the I theta, whatever. And k in k dot x, in here, this is a unit vector along the k direction, and magnitude k, wave number is multiplied. Okay. Speed of light in here, omega over k determines the speed of light. However, it doesn't have to be the same as the speed of light in vacuum. If there is no medium, it is 1. 1, n equals 1 is for vacuum, nothing. And if there is anything, this number is greater than 1. For example, water, glass, that has the refractive index n greater than 1. The speed of light in a medium is smaller than the speed of light in vacuum. And speed of wave can be expressed as the wavelength divided by period. In here, I have indicated the refractive index n. So wavelength depends on the refractive index. Wavelength changes depending on a medium. However, we can see this period and its reciprocal frequency, they do not have argument. That means it is independent of n. You have to remember they are independent, and these are dependent. These are n-dependent factors, and these are n-independent constants. Sure, t may vary depending on the wave. However, even though the propagation of wave through a several media, these t and frequency, the speed of light in vacuum, they are constant. They do not change. And that is a very strong condition. Because of this, wave function becomes continuous. If the frequency changes depending on media, then wave function must break. And there must be, for example, a light wave travels from medium 1 to medium 2. It can be deflected. There's a refraction may appear. However, at this point, the wave function is continuous. The reason is that it actually oscillates up and down, but the frequency of oscillation on the red side and frequency of the oscillation on the blue side, if they are different, then the connection of these two waves will be broken because this oscillates frequently, this oscillates slowly. In that case, there is no way to connect these two continuous lines. However, the frequency is preserved so that even though the path of the propagation may change, the direction of propagation may change, however, the wave function is continuous. That is the direct consequence of the invariance of the period or frequency. Okay, both wavelengths and speed depend on the index of refraction n, and n equals 1 for vacuum. N is always greater than 1 for any other material. Because of that, it appears in the denominator greater than 1. The speed of light in a medium is always slower than the speed of light in vacuum. The reason can be understood as, and actually the light couples to electric charge, and electric charge emits light again. So there is a time delay. Light is absorbed by material. For example, hydrogen atom. It accepts a photon and its energy state is excited. And then it radiates a photon and returns to a lower ground state. Something like that. As the light propagates in vacuum, there is no delay. However, if there are charged particles along the path of light's travel, then this light is absorbed by matter and then radiated from matter again. That makes a delay. That time delay results in the slowdown of the speed of light in a medium. In addition, the formula states that if n is increased greater than 1, it becomes smaller and the period is fixed, so the wavelength of a light wave in a medium is shorter than the wavelength in a vacuum. So wavelength is the perpendicular distance between two nearest wavefronts. Okay, this is a light wave, but actually light wave, it is a widely propagating altogether. So they are traveling like that. So these points are of the same phase, identical phase. If we connect all of the points that has the same common phase, then we say is a wave front. And wave front is perpendicular to the wave vector that designate the direction of propagation. Okay, and there is another wavefronts. So these two are nearest wavefront. Sure, we can choose the lowest value and another lowest value. These two are nearest wavefronts. However, we do not say these two are wavefronts. This is the straight line that connects a single phase, phi equals 0, and next one is phi equals minus 2 pi, something like that. This is phi equals minus pi. So they are not in phase. These are in phase. So these two can be chosen as the nearest wavefronts. The perpendicular distance between the two nearest wavefronts is called the wavelength. So this is a cross-sectional view cutting on this plane. So in this plane, I can find there are two wavefronts are described this way. So perpendicular distance between the two, these are perpendicular distance between the two wavefronts is the wavelength in medium 1. In a similar manner, this is the interface between the two medium 1 and medium 2. If it is going straight, then the speed should be the same. However, the wavelength in medium 2, let's see, this N1 and N2, N2 is greater than N1, such as the case of air and water or glass or vacuum air, something like that. In that case, because of this formula, wavelength in a medium with a greater index of refraction decreases. So this lambda 1 must be greater than lambda 2 in a denser medium. So here we have identified the wavelength inside the medium 2 to be lambda 2. And I told you the frequency and period of oscillation is invariant in two media. That's the reason why this wavefront, this line, this wavefront in medium 1 side and this wavefront in medium 2 side, they meet at a single point, always. That means the wave function is continuous. Okay. We have a common hypotenuse that is a capital represented by capital D, and we have two right triangles, and the wavelengths differ. Using this relation, we can derive Snell's law. Okay, what is a lambda? Coming from a common value. This distance D is a common hypotenuse of the two right triangle. D sine theta. D sine theta. This is D sine theta. Okay, we have a hypotenuse, angle theta 1, and lambda 1, d sine theta. D sine theta equals lambda 1. The angle here, theta 2, the d sine theta is lambda 2. Lambda 2. So d sine theta 2, lambda 2. However, they are different. Only d is an invariant quantity. And we know the angle of incidence. The angle of incidence is represented by this angle. The angle, this is the wave vector K1. This is the wave vector K2. And this is the interface and normal to the interface. So angle between the wave vector and a normal to the interface is called the angle of incidence. And this is refraction, angle of refraction. Sure, there is another, that is angle of reflection. From this relation, d equals lambda 1 over sine theta 1 equals the lambda 2 or sine theta 2. From this, I can rewrite this one to be lambda 1 over lambda 2, and this one appears sine theta 1 over sine theta 2. We know this lambda is inversely proportional to the index of refraction. It should be flipped, but lambda over period is the speed of light. So lambda over period is the velocity. This is Snell's law. So 6 is a simple application to check whether you understand the Snell's law. And another example. And 8 is a non-standard example. There is a gravitation, and we know there is a sliding down without friction, so the velocity changes. But in here, you will find that the point at which the time elapsed becomes minimized is following Snell's law. It is a kind of mechanical Snell's law. So it is our KPOPE's new finding that is published in the Journal of Korean Physical Society. Anyway, if it is not the case and not accelerating, then you can say the Snell's law derived from the constraint that minimize the time delay from A to C via B. And that is called Therma's principle.